Every time you send a blockchain transaction, it feels incredibly simple, doesn't it? You just click send, the transaction processes, it gets added to a block, and boom, the network moves on. But what if I told you that seemingly simple act is actually hiding a massive, invisible infrastructure right beneath the surface? Today, in this explainer, we're going to expose the hidden machinery of Web3. Imagine just freezing that standard send transaction right there on your screen. And let's actually descend beneath the surface. What if every blockchain is secretly performing completely different functions that most of us just mistakenly treat as one big single process? For years, the whole industry just assumed these functions belong together. We built larger and faster chains, sure, but we also inherited these invisible bottlenecks and trade-offs. The real question isn't whether blockchains can scale. It's whether we fundamentally misunderstood how they work this entire time. Now, before we dive deeper into these hidden layers, please note, this explainer on the channel Block Spawns Funds is created for educational and informational purposes only, and does not constitute financial or investment advice. All right, let's get into it. For well over a decade, the blockchain industry operated under what we could call the monolithic illusion. Basically, we treated early blockchains like Bitcoin and Ethereum as singular, giant computers just processing the world's transactions. In a monolithic system, every single full node has to download, verify, execute, and store every single transaction. It's this highly integrated approach that prioritizes simplicity, sure, but it forces one single layer to handle absolutely everything. And as you're going to see, that creates a massive invisible bottleneck. It directly impacts how much you pay in gas fees and how fast your transactions actually clear. So beneath the surface, a blockchain really isn't a single calculator at all. It's much more like a hidden digital metropolis built on 4 distinct pillars. First up is execution, which is all about processing transactions. Second is settlement, which finalizes validity and resolves disputes. Third, we have consensus, which gets the whole network to agree on the order of events. And finally, data availability, which literally guarantees everyone has access to the transaction records. Every single blockchain out there has to perform these 4 core functions. Let's break these down a bit, starting with the execution layer. Think of execution as the massive, churning computational engine of the network. This is where the actual work gets done, It's the calculator that subtracts 10 tokens from your balance and adds them to someone else's. It's where the smart contract logic runs, and where the state of the blockchain is actually updated. But here's the catch. When user demand spikes, this exact engine is the very first thing to overheat in a traditional monolithic design. Now, right beneath execution lies the settlement layer. Once that computational engine does its job, settlement is where those outcomes become permanent. It is the ultimate cryptographic source of truth. So, if execution is where transactions happen, settlement is where their consequences become legally and permanently binding for the network. This is the spot where competing histories collapse into one accepted reality, resolving any disputes and locking those transactions in for good. But here's where the friction completely tears monolithic chains apart. It's called the scalability trilemma. See, you just cannot force every single node to verify, execute, and store every transaction without sacrificing something. If you want maximum scalability to handle all that global demand, you generally have to reduce the number of nodes verifying the chain. And what does that do? It sacrifices security and decentralization. You're constantly being pulled in opposite directions, locked in a zero-sum game. It's kind of like trying to make a car lightning fast, incredibly safe, and cheap enough for literally everyone to own. You almost always have to sacrifice one to get the others. And this exact friction leads us straight to the monolithic breaking point. As global demand rises, that giant computer really starts to struggle. Because every node is out there repeating the exact same work of every other node, congestion spreads like wildfire. Transaction fees absolutely skyrocket, completely pricing out everyday users. And to process more data, well, the hardware requirements to run a node become so exclusionary that only large, centralized operators can even afford them. The system literally breaks under its own weight. Which brings us to a massive aha moment for the entire industry. Instead of one giant machine straining to do absolutely everything, the architecture disassembles. We are separating the stack. Execution decouples from settlement, and settlement separates from data availability. We're transitioning into this incredible, interconnected ecosystem of specialized systems, where each layer is optimized for just one single task. This right here is the paradigm shift from monolithic to modular, and it perfectly mirrors the evolution of traditional software, right? Back when developers moved from those clunky monolithic applications to flexible microservices. A monolithic chain is essentially one network forced to do everything, which usually means doing it poorly when under stress. But a modular architecture? That relies on specialized networks doing one thing perfectly. It completely shatters the hard ceiling on how much a single chain can scale. A perfect example of this specialization is Rollups. Rollups act as our new high-speed execution engines. They take all of that heavy computation completely off the main chain, process thousands of transactions in a specialized environment, and then just post the compressed results back down to a settlement layer like Ethereum. They totally remove the computational burden from the base layer while still inheriting all of its ironclad security. It's a real game changer. So let's track a single transaction as it races through this new ecosystem. First, it executes at lightning speed up in a rollup. Second, it's batched and compressed together with thousands of other transactions. Third, it settles down on a highly secure layer 1, like Ethereum. And finally, the records are published over to a data availability network. It's basically a highly optimized cryptographic relay race. But wait a second. Separating all these layers creates a totally new hidden vulnerability. What happens if the data goes missing? If execution and consensus live somewhere else entirely, someone has to guarantee that the transaction data actually exists and can be retrieved, right? This is known in the industry as the data availability problem. Think of this as endless oceans of data. If a malicious block producer hides the transaction data but still publishes the block header, the whole network is basically paralyzed. Without that underlying data, light clients, which are just regular users on everyday devices, cannot verify if the state changes on the rollup are actually legitimate. They literally can't recreate the state. If the records are withheld, execution and settlement entirely lose their meaning. It makes the network completely unverifiable. So how on earth do we solve this without forcing every single node to download terabytes and terabytes of data? The answer is data availability sampling, or DAS. It relies on this brilliant mathematical trick called erasure coding. Think of it like checking just a few random pieces of a massive jigsaw puzzle to mathematically guarantee that the whole picture is actually in the box. It allows lightweight nodes to verify that the entire block is available simply by checking small random fragments. It gives you absolute cryptographic assurance, totally bypassing the massive hardware overhead. And this breakthrough leads us to the immense power of dedicated data availability layers like Celestia or Eigenday. Because they're completely decoupled from execution, they enable what's called sublinear block validation. Basically, this means everyday users can provide robust security using just mobile phone level hardware. And here is the mind-bending part. Rather than slowing down, the transaction throughput of these DA networks can actually increase as more nodes join the network. The economic impact of this modularity is just massive resource efficiency. By decoupling these core functions, developers no longer have to bootstrap an entire validator set from scratch just to launch a blockchain. They can pool security and hardware by plugging straight into a shared data availability layer, snapping together proven shared infrastructure components just like Lego blocks. Launching a new highly secure app chain becomes almost totally frictionless. Okay, so let's reframe our mental model entirely. These are the new rules of blockchain. Execution decides what happens. Settlement decides what becomes permanent. Consensus agrees on the order, and data availability decides if anyone can actually verify it. For years, these functions were treated as one single, struggling machine. But the future clearly belongs to architectures that recognize they were never the same thing to begin with. Which leaves us staring right into the vast, modular future of Web3 infrastructure.
is blockchains are no longer bound by the limits of a single giant computer. If they're now highly specialized, interconnected cryptographic universes operating in perfect harmony, what limits what we can build next? Honestly, as data barriers fall and execution speeds soar, the only limit left might just be our imagination. Thank you so much for joining me on this explainer, and keep exploring the architecture of tomorrow.